Good evening, everyone. This is Nagashasan Galapati, and I have here Srika Shupari Satyanarayana with me here. So, this is a homework video for course Design and Analysis of Reconfigurable Systems. In this homework, we were told to implement a 1-bit full adder using Intel Quartus Prime Lite and a QuestaSim to verify the adder behavior. To do that, first we have to install the Quartus Prime Lite. So, I went ahead and done that. This is the whole UI of the Quartus Prime Lite edition. And also, we have to obtain a license for QuestaSim to run the simulations and to verify the behavior. I went ahead and done that as well. Now, after starting up the Quartus Prime Lite, it's going to show it like this. Now we have to create an empty project. So to do that, click on the new project wizard. Once you click on that, click on next. Give a project name, let's say full adder 4. Click on next. Select the empty project type. Click on next. Click on next. And the device family you're using is like Cyclone 5. Click on it's already selected. The device we are using the F31C6. Now go ahead and search for that. Yeah, this one. Select this. Click on next. Click on next. Now click finish. Now it's going to open the empty project. Let's wait for that. So this is the whole empty project window. Here we have to create a schematic and save as your project name.bdf by inserting the gates, wires on the canvas using library and rename the pins and compile the design. So now we're going to do that. Now to do that, click on file and click on new. Once you clicked on the new, under design file, select block diagram/schematic, click on OK. Now it's going to open this empty canvas for you to draw the schematic. To do that, double click on the canvas. Once you double click on the canvas, scroll under primitives, expand that, go to logic and expand that. So as you can see here, there are a list of many gates that we can use. Select the gates and click on OK. So for a full adder, we need AND gate, XOR and OR gate. Repeat the procedure by double clicking the canvas and complete the schematic. Now I'm going to go ahead and do that. So I've gone ahead and completed the schematic by inserting the ports, nets, wires and etc. And I've renamed them A, B, C in and output as sum and carry out. Now we need to save this project or save the schematic by the format of .bdf. I went ahead and done that as well. Once this is done, you have to compile the whole design and verify the report according to the description.
For part 1 of the assignment, we are going to go ahead and compile our synthesized Verilog file. After the compilation is done, as you can see the compilation report, the ALMs used are 2 and the total pins used are 5 for 1-bit full adder. And in the resource usage, we can see combinational ALUT usage for logic is 2 and IO pins are 5. Now for the timing analysis, open the timing analyzer, go to custom reports and report path. Click OK. So the maximum delay is observed from pin A to the sum with a delay of 6.64 and the maximum frequency is 1/6.64 nanoseconds. This is the critical path for operating conditions slow 1.1 volts and 85 Celsius model. Now going back to Quartus menu and run the simulation using RTL simulation. Open Questa and compile the test bench file. Recompile both of the source files and the test bench file. As you can see, without errors and warnings, we have successfully compiled test bench and the source. Now simulate the test bench, add the required signals to the wave, and run simulation. This is the test bench that is used for the verification of 1-bit full adder. As you can see, the initialization values are all 0, and the test vectors are used from 0, 0, 0 to max, that is 1, 1, 1, including the carry in pin. Let us go and check few samples for verifying our 1-bit full adder. Taking this example, our input A is 1, B is 0, carry in 0. So the sum is expected to be 1 and the carry out should be 0. Taking one more example, in this case, A is 1, B is 0, carry in is 1. So the sum should be 0 and carry out should be 1. By this, we have successfully verified our 1-bit full adder. Now we go ahead and remove our synthesized Verilog file and load our RTL Verilog. As you can see, this is the RTL Verilog which is written in behavioral mode. So we go ahead and compile this. So after compiling our behavioral 1-bit full adder, we get the flow summary. The total ALMs used are 2 and the total pins are 5, which is same as the schematic. Going to the resource usage summary, we can see the combinational ALUT usage for logic is 2 and the IO pins are 5. And for timing analysis, open timing analyzer and report path. Click OK. As you can see, the maximum delay or the critical path is from C in to the output sum, the delay of 6.64, and the max frequency is 1 over 6.64 nanosecond. Close timing analyzer and open Questa for simulation. Simulate the test bench and run the simulation. Here we are using the same test bench that we verify for 1-bit schematic input. So let us go ahead and check 2 more samples. Considering this scenario, our input is 1, A is 1, B is 0, C in is 1. So the output should be 0 and the carry out should be 1. Taking one more example, A is 1, B is also 1, C in is 0. So the output should be 0 and C out should be 1. So we have successfully verified our RTL 1-bit full adder. For the part 3 of the assignment, we are going to verify 4-bit structural and behavioral full bit adder. Starting with the behavioral model, as you can see, this is the behavioral RTL of the 4-bit full adder. We are going to go ahead and compile the design. The compilation is done. As you can see in the flow summary, the ALM units used are 3 and total pins used are 14. And in the analysis, you can see the resource usage summary. The combination ALUT usage for logic is 5 and the IO pins used are 14. As per the timing analysis, open timing analyzer and report path. As you can see, the critical path is from one of the inputs first bit, in this case B input 0, to the sums output at S2 with a delay of 8.284 nanoseconds. So the maximum frequency is 1 over 8.284 nanoseconds. Close the timing analysis and open Questa for verifying our 4-bit full adder behavior. This is the test pins that is used for verifying the functionality of the 4-bit full adder. Assign some random inputs to the inputs of the adder and for the the carry in of the adder. As you can see, the compilation ran successfully without errors and warnings. Now simulate the design. Add the necessary signals to the wave and run simulation. Convert the output radix into unsigned so that we can see the adder in action. Let us take 2 random samples so that we can verify our adder behavior. The input is 9, the second input is 2, and the carry in is 1. So the output should be 12 and with the carry out of 0. So this is verified. Let us take one more example. The input 1 is 13 and input 2 is 5 and the carry is 1. The expected value should be around 19, but the carry overflows, so we get the sum of 3 and carry out as 1. So we have successfully verified our 4-bit full adder in behavior mode. Close the simulation and load the next Verilog file. Remove the file, from the project and add the structural RTL of the 4-bit full adder. As we can see, this is the full adder 4-bit full adder in structural mode. So we go ahead and compile the design. Set as top level entry and compile the design. After compilation, as we can see in the flow summary, the logic utilization in ALMs is 4 and total pins used are 14. In the analysis, we can go to the resource usage summary and we can see the combinational ALUT usage for logic is 6 and the IO pins are 14. As for the timing analysis, open timing analyzer and report path. So the critical path in the 4-bit full adder is from C in to C out with a delay of 7.98 7.985 nanoseconds. And the maximum frequency is 1 over 7.985 nanoseconds. Close the timing analysis and open Questa for simulation. We are using the same test bench that we verified for the 4-bit behavioral full adder. So we compile the designs. As you can see, with no errors and warnings, we have successfully compiled it. Now simulate the test bench, add the necessary signals to the wave and run simulation. Convert the output radix format into unsigned. Now let us take two examples to verify our behavior. The input, one of the inputs is 6 and other is 4 with a carry in of 1. So the total sum should be 11, which is verified, and the carry out is 0. Now let us take another example. The input 1 is 9 and input 2 is 8 with a carry in of 1. The sum should be expected at 17. So the carry out is 1 with the sum output of 2. So the value, so the behavior of the 4-bit full adder in structural form is also verified. Coming back to Quartus, if we open the coming back to Quartus, we can see the logic utilization for structural is 4 ALMs instead of 3 that is synthesized from the behavioral Verilog. This implies that the logic synthesis is better at optimizing and reducing usage of ALMs. Thank you for watching.